Welcome to this video on two-dimensional random variables. We have already seen about one-dimensional random variables in the prior videos. Now, what is going to be an one-dimensional random variable? It is nothing but a mapping or a function that takes the elements of the sample space and maps it to a real number system. Now, in all the time, we need not be of interest or be concerning about just one variable. More than one variable can be involved in my experiment, which is going to be of interest to us. So say suppose both voltage and current might be of interest in a certain experiment. So when the number of variables of interest increases, then the dimension of the random variable also increases. So this session will be dealing with two-dimensional random variable, where instead of just a single variable x, we will be dealing with two variables x and y. So we will define a two-dimensional random variable. Let S be a sample space which is being associated with a random experiment E. Now we are going to have x to be a function that takes the elements of the sample space, as well as y to be another function which takes the elements of the sample space. So now each of these functions, what they are going to do, they are picking an element from the sample space and each of them are assigning it to a real number. So if this is going to be the case where these two functions each assign a real number to the outcome S that belongs to your sample space, then the ordered pair x comma y will be referred by the name two-dimensional random variable. So both x is also going to take an element of S and assign it to real number. Y is also going to take the element of the sample space and assign it to a real number. In which case the ordered pair will be called as a two-dimensional random variable. As we classified the one-dimensional random variable, the two-dimensional random variable will also be classified into two categories. The first category is a discrete two-dimensional random variable, and the second part being the continuous two-dimensional random variable. Now let us quickly recollect what is meant by a one-dimensional discrete random variable. Then we will be able to correlate the data which we have already learned to that of two-dimensional. When we had a one-dimensional random variable, we saw that we defined a probability mass function which was defined by the condition that the individual probability pi must be greater than or equal to 0, and the second condition is that when we add all the pi, the total sum must be equal to 1. This is for a one-dimensional random variable. Similarly, for the continuous case, we defined a probability density function where for the one-dimensional random variable, we had the first condition that f of x must be greater than or equal to 0 for all the values of x that belong to the real number system, and the second condition is that minus infinity to infinity f of x dx is equal to 1. So this is again for a one-dimensional random variable. Now how can we extend this concept to two dimension? Now instead of just one x which was distributed as a table like this, now we have an x as well as an y which is going to be distributed in the table of this format. So an variation in x as well as an variation in y. So what we get as an output for a discrete two-dimension random variable will be a table or a matrix kind of structure. And this table or the matrix which we are going to form again is going to follow two rules, simple rules like this. So this is just an extension of this one-dimension random variable which we have already studied. Now what are going to be those two rules? So for a discrete two-dimension random variable, we define the joint probability mass function. Instead of the probability mass function, we define joint probability mass function. So what is this joint probability mass function? Now x is going to take the value xi and y is going to take the value yj. This is denoted by the probability Pij. Now this probability Pij will now be following two conditions, just like our prior case. What was the first case? Individual probability must be greater than or equal to 0 and it has to be less than or equal to 1. Similarly, the combined probability Pij will again be greater than or equal to 0 for all the values of I and j. Now what did we see in one dimension? Summation of the total probability must be equal to 1. That is, addition of all the probabilities must be equal to 1. Now this was only along a row. Now we have a column also. So what happens now? Instead of one summation, we have two summations Pij equal to 1. For this, the first summation runs for the row and the second summation runs for the column. So the two conditions for a joint probability mass function is that the probabilities of x and y together, which we denote as Pij, must be greater than or equal to 0, and when you add all the probabilities along the row as well as along the column, then the total probability must be equal to 1. Now, instead of a single row wise, now what happens when I am going to input? Now this is the variation in x. My capital X is going to take the values x1, x2 up to say xn. And my capital Y is the second random variable that is going to take the value y1, y2, y3 up to say ym. Now the combination of one x with one y will give me the probability P11. Next, the probability of, that is, x taking the value x1 and y taking the value y1 is nothing but my P11. Now the combination of x1 with y2 will give you P12 and x1 with y3 will be P13, and so on. We can compute up till P1m. So P1m is x taking the value x1 and y taking the value ym. So this is going to be the probability. So in such a way, if we are going to fill, now y taking all the values from y1, y2 up to yn, x taking the value x1, x2 up to xn. So what we will be getting is a table or a matrix of probabilities, and over here all these individual probabilities must be greater than or equal to 0, and when you add up all the datas inside this, what must be the total sum? The total sum must be equal to 1. Okay, so this is for a discrete case. Now how about the continuous case? What did we see for a continuous case of a one dimension? The function f of x must be greater than or equal to 0 for x belonging to our real number system. And integral from minus infinity to infinity f of x dx, when I add up or integrate up all the data from minus infinity to infinity over the range space, then what happens? The total sum must be equal to 1. Now instead of one dimension x, now we have two dimension. So in which case what will happen to our f of x? This f of x will now become f of x comma y. So one variation for x, the other variation for y. So the function will be a function of two variables, an x and y. Now how can we associate the same quantity f of x comma y with these two properties? So in which case what happens is, this now gets defined as continuous two-dimensional random variable, and we call it by the name joint probability density function. Now the criteria to be satisfied by our f of x comma y is that you call this f of x comma y as a joint probability density function if it satisfies the condition number 1, f of x comma y is greater than or equal to 0 for all the values of x and y that belongs to the range space or the real number system, and minus infinity to infinity, f of x comma y dx dy will be equal to 1. Now the first integration is for x, the second integration is for y. So whatever quantity we have defined for one variable, the same concept we have now just extended it for one more variable. And what do we call it as? We call it by the name joint probability mass function and joint probability density function. I hope that the extension from 1 to 2 dimension is going to be clear from these two definitions. Now we move on to the next quantity called as marginal probability function of x and marginal probability function of y. That is, we are going to find what is the variation of x when x is going to be fixed and y takes all the values that varies from y1 to ym. And in a similar way, we can keep our y fixed and then vary for all the variations of x varying from x1 to xn. So in which case, where you keep your x fixed, and consider just the variation in y1, y2, y3 up to yn, then such a probability is called as marginal probability function of x. So which is fixed here? X is fixed, which is varying, y is varying. So I write it as pi1, pi2, pi3 up to pin. So this is denoted by the symbol pi and a dot. Okay, so pi dot stands for the marginal probability function of the random variable x. Now for your y, what is kept as fixed? Y is kept as fixed, which is varying. X varies as x1, x2, x3 up to xn. So the variation is in which quantity? X varies. So you write it as the variation is given for x. So you place a dot for x, and which is kept fixed? J is kept fixed. So P dot J represents the marginal probability function of the random variable y. So now if we are going to apply this to the matrix or the table which we just now defined, then what will happen? So we will have x1. So this x1 is fixed. We have, considering the variation of y1 varying, y2 varying, y3 varying, and so on, yn varying. So what you will be getting is this quantity which is fixed. 1 is fixed, which is varying, your y is varying. So you define your p1 dot. Now in the second quantity which is fixed, x2 is fixed, which is varying, your y is varying. So when your y varies, what you will be getting is p2 dot. Now in a similar way, when your n is fixed and your y is varying, what you will be getting is going to be your pn dot. This collection where your x is fixed and your y varies is called as marginal probability function of x. Now consider the other way around. What is going to be the other way around? What is kept fixed? Y is going to be fixed, which is varying, your x is going to vary. So when y is going to be fixed and x is varying, you consider this as p dot 1. So which is varying? Y dot is going to be x, x is varying. Now what is fixed? Y is fixed, which is varying, again your x is varying. So this is p dot 2. Now for the third quantity which is fixed, your y is fixed, your x varies. So x varies as p dot 3. So if we move on in such a way, we will be getting p dot m, and this collection of probability which you have over here will be referred by the name marginal probability function of y. Now this first quantity is defined as probability of x equal to x1. The second quantity is defined as probability of x equal to x2. The last one is defined as probability of x equal to xn. Similarly, what can we say about the quantity over here? This point is called as probability of y equal to y1. The next one is probability of y equal to y2. The next one is probability of y equal to y3, and so on. What will this now be equal to? Probability that y equal to ym. So in this way, your individual probabilities which are estimated are referred by the name marginal probability function of x and marginal probability function of y. Now there is going to be a special case called as independence. What happens if x and y are independent. What do we mean by the name independent? X doesn't depend on y doesn't depend on x. X can act separately, y can act separately. Any variation in x does not affect y and any variation in y does not affect x, in which case you call x and y are independent. And when they are independent, what can we say about their marginal functions? Then the probability Pij is nothing but the product of their individual marginal probability function of x and marginal probability function of y, in which case your P11 is nothing but probability of x equal to x1 into probability of y equal to y1. Your Pij will be equal to probability of x equal to xi and probability of y equal to yj. So when you take any element inside the matrix and multiply with its corresponding marginal probabilities, then that will be equal to the element over here. So this is how we define the marginal probability functions of x and marginal probability functions of y.